than not knowing anything. But it's not necessarily enough to tell the commander exactly what needs to be done in order to protect troops, in order to continue the mission. And the interest is in unburdening the warfighter and continuing the mission. So putting everybody in Mach 4 isn't going to get you there. So what we need to understand, as opposed to being aware, is exactly what does this mean? When a sensor goes off, what's the impact on my mission? And what do I have to do to mitigate that impact so that I can continue that mission as in an unburdened way, in as much of an unburdened way as possible? Obviously, there's always going to be an impact. Anytime you get attacked by any sort of a weapon, there's an impact on your mission. But it's mitigating that in a way that allows you to continue the mission with as little burden as possible, as that's what our interest is in. So we partnered with the Night Vision Laboratory because they're developing this thing called the Integrated Sensor Architecture. That's the first kind of layer of our layered sensing initiatives, the ability to pull in context information from all the sensors that are in your AO, your area of operations. And the integrated sensor architecture is being adopted by the Army into its sensor computing environment, which is part and parcel of the future common operational environment that the Army will go to war with. That allows interface between command and control systems, intel systems, force protection systems, the mobile and handheld, and the mounted systems that are out on the battlefield today. The integrated sensor architecture is designed to be on the tactical edge, a compact set of code that allows for a publish and subscribe environment for all sorts of sensors. Enabling a sensor with ISA gives it the ability to be discovered essentially on any C2 environment, any command and control environment. And that sensor's identity, metadata that goes with it, its state, can all be pulled into the system and then analyzed for further understanding of what's going on. So this is the Army's common operational environment. It's what the G6 has mandated the Army's going forward with, and it is going into version 3 as an IOC, given the capability production document that's in place. So it is real. There is an actual Army architecture that leverages the integrated sensor architecture. The vision is to be able to pull in data. We call it the green ring, blue ring, and despite the fact that your system may have a preference, you may have sensors that are dedicated to artillery detection or counter rocket and artillery and mortar. Those sensors are going to be pulling information on the ground level, and they're pushing that information to a dedicated system like a FADEDS. However, you're also able to pull the data in from the AFADEDS level and publish that to other systems that are connected to that same architecture, so that you're able to exchange information from all these disparate systems. And that kind of data is very useful. In the chem-bio sensor community, we are interested in knowing when there's some sort of an incident that happened. We have an example in our booth here where we have a surveillance system, the Scout. It's simply a camera that just is slews to Q. It's normally partnered with a ground surveillance radar, so it can detect any kind of activity on your perimeter, slews to Q to get some visuals on it, and then it alerts you to the presence of something that's surreptitious. And that allows us to then queue other assets, including our mobile version of the chem-bio sensors. Now, we're going from the chem-bio sensors that have been normally developed kind of in a stovepipe sense. There's a special box, there's a special shape for the box. It's been designed for whatever purpose that particular sensing element has. And now we're going to a more modular architecture that allows us to plug and play. These can be then mounted onto a tripod, or it can be mounted onto a mobile platform, as we demonstrate in our booth here with the quadcopter, carrying the same sort of payloads. And we can do this for both chemical and biological sensing. And they also carry on board the ability to sample on cue. Either you remotely trigger the sampler, or it can be triggered automatically when there's a detection event by your sensor. So that allows the interface of these systems and the use of modern autonomy and control to unburden the warfighter. Now you don't actually have to pilot this bird or move this sensor around. It's done automatically, and the system takes advantage of artificial intelligence and autonomy in order to achieve that. So integrated early warning is a direction now that the Chem Bio Defense Program is moving. It's taking advantage of this capability to integrate systems, to develop these layered architectures, and pull in information from disparate sources to develop context, and go through and undertake a series of computational analytics on what we call sensor data analytics, and we'll talk about that a little bit more. And I'd certainly invite you to come over to the display so that we can demonstrate what sensor data analytics looks like and how it provides value in terms of situational understanding for the warfighter. So here it is, the Cerberus Scout. We have the camera part of it, but not the radar part. An example display is shown here where we went to Dugway Proving Ground, and the disseminator truck went out there, turned on its disseminator, started to spew an aerosol into the air. The infrared camera is able to pick up some signatures of these aerosols, and that gave us our first cue. Well, something is odd here. This isn't one of our trucks. It's in an area that should be denied, and there they are. Now they're spraying something in the air. So there's kind of a lot of dead giveaways here, but it still allows us to develop a picture, exactly what's going on, and then we can layer that on top of other information that we're generating from other sources. One source, and I have a demonstration again at the booth that shows some of the data products of this, the iSafe 1.5 micron LiDAR system. It reaches out with a laser beam and it pulls back data from scattering off of particles. And that allows it to actually develop a physical map of the plume as it travels through space. And then it can actually monitor the motion of that plume through space to develop these things that we call wind vectors. And it does that at a certain resolution in space to develop an entire field of wind vectors. And that's going to be useful for a lot of things besides just what we're doing with it. Of course, the Chem Bio defense community wants to know what wind vectors are out there, because that tells us if there's a threat plume, a poison cloud, or biological hazard, it's moving through space at the whims of these wind vectors. So these are what's telling us where it's going to be in 2 minutes time and in 5 minutes time and how it disperses through space. But it's also this kind of data that's useful to other communities, such as the folks that are doing artillery or long-range ballistics, missiles. There's a lot of folks that are interested in the capabilities developed by this system, so that it has a multiple functionality. The boxes that do sensing are still part of the architecture because they're still going to be out there in quantity. The difference is that we're bringing them together and we're networking them. And we're adding some capability in terms of GPS and metadata sensing to be part of the package so that when it all comes together, we can do some analytics on that data. And as I mentioned, we're working towards this modular framework. This is the Acorns, which is the array configurable of remote network sensing. It's one approach to allow us to take all these different types of sensors and bring them together in a plug-and-play architecture and allow us to modular. We can configure for whatever particular mission we're interested in the sensing package that we need. And here it is with the Acorns mounted on the Deep Purple. We have the Deep Purple here. You can come take a closer look at it. Just a quadcopter that allows for that autonomous movement of the sensor through space. And that allows us to cross-cue that sensor and intercept plumes and do this sort of interrogation. And as I mentioned, it can also turn on a sampler, collect a sample, bring that sample back so you can do further analysis on the threats. Then it all comes together. This is where coming to see the actual live display of the sensor data analytics will pay dividends. And Scott McGill from Arete is here to show how his company has developed some extensively involved analytics involving Bayesian statistics and other computational tools that bring all this information from these different types of sensors together and pulls the metadata out, pulls any LiDAR data if you have that out, and fuses it all together, and then goes through and compute what we call a source term. So we can take things like, well, what did the radar say? The radar said there was some sort of movement here. The camera says there was some weird cloud coming off of that truck. Well, that gives you a location. If you don't even have that, you can still use data from the wind vectors and the sensors themselves to be able to pull out an understanding of what that source term was that led to that detection event. And it also helps with further analysis can allow you to reduce false alarms, because if a sensor is just sort of flickering on and off and it gives you an occasional alert here and there, but it doesn't correlate with any of the wind fields that you have in your AO, and none of the other sensors are agreeing with it, or they don't agree in a way that's consistent with the wind fields, then you can start to suppress some of these false alarms that these sensors have the propensity to generate. Another point on the analytics is that we now are able to inform the operators about the impact. It's not just that you have a sensor going off or one or two sensors going off, it's that you have a sensor going off and it's generating information that it conveys to the decision maker. What's the impact of this? How can I respond to this? This tells me now there's an alert. There's an alert that correlates to some source term, that there's a likely location where this release occurred. And now there's an alert that's generating a path on the ground, which is most likely affected by the high concentration areas of that attack. And that allows me to very, very cleanly define the impact on my operation of this attack, as opposed to a bunch of blinking red sensors all around my AO, and I'm trying to make some sense of it. So that takes it a step further. To take it even a step further, and we can demonstrate that again if you come out to our booth and take a closer look at the technology, you can actually take this sensor alert, as illustrated in this diagram by this red line that connects all these sensors. You basically built a web of sensors, or an internet of sensors, if you will. They're all connected together, and the correlation and the analysis that's going on behind them is allowed to get into that data and actually pull out alerts at the network level. And a network alert can be detected even before the sensor itself will alert at its threshold. So we're able to pull signature information off of those sensors and again correlate it to the met conditions and the movement of the air mass and all that, and pull out an alert state even before any of the sensors themselves go off. And in fact, when we went to Dugway out in August, we were able to demonstrate that with 6 minutes before any of the sensors went off, we pulled a network alert that indicated the presence of a threat. So at the end, the Integrated Early Warning Program is a future direction for the Chem Bio Defense Program. It's being pursued by the Defense Threat Reduction Agency, which is my customer, Joint Science and Technology Office, but it's also being pursued in parallel by the Joint Program Office for Joint Program Executive Office for Chemical and Biological Defense. They've got their own initiative, an enhanced capability demonstration that's going to take a lot of the technology that we generate and bring to a certain maturity level and continue to mature it, make it more mature for eventual transition into a program of record. And then today it was the outbrief actually from the Joint Requirements Office, in which they presented to the community the analysis of the capabilities-based assessment behind integrated early warning. They've had a team studying this for several months at the order of the DASTE, the Deputy Assistant Secretary of Defense for Nuclear, Chemical, Biological, to take a look at, deep dive, do a capabilities-based assessment of what does this integrated early warning contribute to our warfighters' ability to operate in a chemical, biological environment, and tell us what you recommend. So I'm looking forward to the outcome of that briefing. I wasn't able to attend it, but I'm glad I was here today to give you a picture of what this is and where we're going with it. And end state, improved awareness and understanding, timely decision making. So it's moving from awareness to understanding and providing that information that decision makers, commanders need to make force protection decisions. Subject to your questions, that's a quick nutshell briefing of what integrated early warning and the layered sensing initiative is all about. All right, any questions? All right, well, please come see our technology.